An organic light-emitting diode is a light-emitting diode in which the emissive electroluminescent layer is a film of organic compound that emits light in response to an electric current. This layer of organic semiconductor is situated between two electrodes. Typically, at least one of these electrodes is transparent. OLEDs are used to create digital displays in devices such as television screens, computer monitors, portable systems such as mobile phones, handheld game consoles and PDAs. A major area of research is the development of white OLED devices for use in solid-state lighting applications. There are two main families of OLED, those based on small molecules and those employing polymers. Adding mobile ions to an OLED creates a light-emitting electrochemical cell which has a slightly different mode of operation. OLED displays can use either passive matrix or active matrix addressing schemes. Active matrix OLEDs require a thin film transistor backplane to switch each individual pixel on or off, but allow for higher resolution and larger display sizes. An OLED display works without a backlight, thus, it can display deep black levels and can be thinner and lighter than a liquid crystal display. In low ambient light conditions, an OLED screen can achieve a higher contrast ratio than an LCD, regardless of whether the LCD uses cold cathode fluorescent lamps or an LED backlight. History. André Barnos and co-workers at the Nancy Université in France made the first observations of electroluminescence in organic materials in the early 1950s. They applied high alternating voltages in air to materials such as acridine orange, either deposited on or dissolved in cellulose or cellophane thin films. The proposed mechanism was either direct excitation of the dye molecules or excitation of electrons. In 1960, Martin Pope and some of his co-workers at New York University developed ohmic dark injecting electrode contacts to organic crystals. They further described the necessary energetic requirements for hole and electron injecting electrode contacts. These contacts are the basis of charge injection in all modern OLED devices. Pope's group also first observed direct current electroluminescence under vacuum on a single pure crystal of anthracene and on anthracene crystals doped with tetracene in 1963 using a small area silver electrode at 400 volts. The proposed mechanism was field-accelerated electron excitation of molecular fluorescence. Pope's group reported in 1965 that in the absence of an external electric field, the electroluminescence in anthracene crystals is caused by the recombination of a thermalized electron and hole, and that the conducting level of anthracene is higher in energy than the exciton energy level. Also in 1965, Helfrich and W. G. Schneider of the National Research Council in Canada produced double-injection recombination electroluminescence for the first time in an anthracene single crystal using hole and electron injecting electrodes, the forerunner of modern double-injection devices. In the same year, Dow Chemical researchers patented a method of preparing electroluminescent cells using high-voltage AC-driven electrically insulated 1 mm thin layers of a melted phosphor consisting of ground anthracene powder, tetracene, and graphite powder. Their proposed mechanism involved electronic excitation at the contacts between the graphite particles and the anthracene molecules. Roger Partridge made the first observation of electroluminescence from polymer films at the National Physical Laboratory in the United Kingdom. The device consisted of a film of poly up to 2.2 micrometers thick located between two charge-injecting electrodes. The results of the project were patented in 1975 and published in 1983. Ching W. Tang and Stephen Van Slyke at Eastman Kodak reported the first OLED device in 1987. This device used a novel two-layer structure with separate hole transporting and electron transporting layers such that recombination and light emission occurred in the middle of the organic layer. This resulted in a reduction in operating voltage and improvements in efficiency that led to The current era of OLED research and device production. Research into polymer electroluminescence culminated in 1990 with J. H. Burrows et al. At the Cavendish Laboratory in Cambridge reporting a high-efficiency green light-emitting polymer-based device using 100 nanometers thick films of poly. Universal Display Corporation holds the majority of patents concerning the commercialization of OLEDs. Working principle. A typical OLED is composed of a layer of organic materials situated between two electrodes, the anode and cathode, all deposited on a substrate. The organic molecules are electrically conductive as a result of delocalization of pi electrons caused by conjugation over part or all of the molecule. These materials have conductivity levels ranging from insulators to conductors, and are therefore considered organic semiconductors. The highest occupied and lowest unoccupied molecular orbitals of organic semiconductors are analogous to the valence and conduction bands of inorganic semiconductors. Originally, the most basic polymer OLEDs consisted of a single organic layer. One example was the first light-emitting device synthesized by J. H. Burrows et al., which involved a single layer of poly. However, multi-layer OLEDs can be fabricated with two or more layers in order to improve device efficiency, as well as conductive properties. Different materials may be chosen to aid charge injection at electrodes by providing a more gradual electronic profile, or block a charge from reaching the opposite electrode and being wasted. Many modern OLEDs incorporate a simple bilayer structure, consisting of a conductive layer and an emissive layer. More recent developments in OLED architecture improves quantum efficiency by using a graded heterojunction. In the graded heterojunction architecture, the composition of hole and electron transport materials varies continuously within the emissive layer with a dopant emitter. The graded heterojunction architecture combines the benefits of both conventional architectures by improving charge injection while simultaneously balancing charge transport within the emissive region. During operation, a voltage is applied across the OLED such that the anode is positive with respect to the cathode. Anodes are picked based upon the quality of their optical transparency, electrical conductivity, and chemical stability. A current of electrons flows through the device from cathode to anode. As electrons are injected into the LUMO of the organic layer at the cathode and withdrawn from the HOMO at the anode. This latter process may also be described as the injection of electron holes into the HOMO. Electrostatic forces bring the electrons and the holes toward each other and they recombine, forming an exciton, or bound state of the electron and hole. This happens closer to the emissive layer, because in organic semiconductors holes are generally more mobile than electrons. The decay of this excited state results in a relaxation of the energy levels of the electron, accompanied by emission of radiation whose frequency is in the visible region. The frequency of this radiation depends on the band gap of the material, in this case the difference in energy between the HOMO and LUMO. As electrons and holes are fermions with half-integer spin, an exciton may either be in a singlet state or a triplet state depending on how the spins of the electron and hole have been combined. Statistically, 3 triplet excitons will be formed for each singlet exciton. Phosphorescent organic light-emitting diodes make use of spin-orbit interactions to facilitate intersystem crossing between singlet and triplet states, thus obtaining emission from both singlet and triplet states and improving the internal efficiency. Indium tin oxide is commonly used as the anode material. It is transparent to visible light and has a high work function which promotes injection of holes into the HOMO level of the organic layer. A typical conductive layer may consist of PEDOT, PSS as the HOMO level of this material generally lies between the work function of ETO and the HOMO of other commonly used polymers, reducing the energy barriers for hole injection. Metals such as barium and calcium are often used for the cathode as they have low work functions which promote injection of electrons into the LUMO of the organic layer. Such metals are reactive, so they require a capping layer of aluminium to avoid degradation. Experimental research has proven that the properties of the anode, specifically the anode-hole transport layer interface topography, plays a major role in the efficiency, performance, and lifetime of organic light-emitting diodes. Imperfections in the surface of the anode decrease anode organic film interface adhesion, increase electrical resistance, and allow for more frequent formation of non-emissive dark spots in the Oled material, adversely affecting lifetime. Mechanisms to decrease anode roughness for ethos glass substrates include the use of thin films in self-assembled monolayers. Also, alternative substrates and anode materials are being considered to increase Oled performance and lifetime. Possible examples include single crystal sapphire substrates treated with gold film anodes yielding lower work functions, operating voltages, electrical resistance values, and increasing lifetime of OLEDs. Single carrier devices are typically used to study the kinetics and charge transport mechanisms of an organic material and can be useful when trying to study energy transfer processes, as current through the device is composed of only one type of charge carrier, either electrons or holes. Recombination does not occur and no light is emitted. For example, electron-only devices can be obtained by replacing ethos with a lower work function metal, which increases the energy barrier of hole injection. Similarly, hole-only devices can be made by using a cathode made solely of aluminium, resulting in an energy barrier too large for efficient electron injection. Material technologies. Small molecules efficient OLEDs using small molecules were first developed by Dr. Ching W. Tang al. at Eastman Kodak. The term Oled traditionally refers specifically to this type of device, though the term Oled is also in use. Molecules commonly used in OLEDs include organometallic chelates, fluorescent and phosphorescent dyes, and conjugated dendrimers. A number of materials are used for their charge transport properties. For example, triphenylamine and derivatives are commonly used as materials for hole transport layers. Fluorescent dyes can be chosen to obtain light emission at different wavelengths, and compounds such as perylene, rubrene and quinacridone derivatives are often used. AlQ3 has been used as a green emitter, electron transport material, and as a host for yellow and red emitting dyes. The production of small molecule devices and displays usually involves thermal evaporation in a vacuum. This makes the production process more expensive and of limited use for large area devices than other processing techniques. However, contrary to polymer-based devices, the vacuum deposition process enables the formation of well-controlled, homogeneous films, and the construction of very complex multi-layer structures. This high flexibility in layer design, enabling distinct charge transport and charge blocking layers to be formed, is the main reason for the high efficiencies of the small molecule OLEDs. Coherent emission from a laser dye-doped tandem Oled device, excited in the pulsed regime, has been demonstrated. The emission is nearly diffraction limited with a spectral width similar to that of broadband dye lasers. Researchers report luminescence from a single polymer molecule, representing the smallest possible organic light-emitting diode device. Scientists will be able to optimize substances to produce more powerful light emissions. Finally, this work is a first step towards making molecule-sized components that combine electronic and optical properties. Similar components could form the basis of a molecular computer. Polymer light-emitting diodes, also light-emitting polymers, involve an electroluminescent conductive polymer that emits light when connected to an external voltage. They are used as a thin film for full-spectrum color displays. Polymer OLEDs are quite efficient and require a relatively small amount of power for the amount of light produced. Vacuum deposition is not a suitable method for forming thin films of polymers. However, polymers can be processed in solution, and spin coating is a common method of depositing thin polymer films. This method is more suited to forming large area films than thermal evaporation. No vacuum is required, and the emissive materials can also be applied on the substrate by a technique derived from commercial inkjet printing. However, as the application of subsequent layers tends to dissolve those already present, formation of multi-layer structures is difficult with these methods. The metal cathode may still need to be deposited by thermal evaporation in vacuum. An alternative method to vacuum deposition is to deposit a Langmuir-Blodgett film. Typical polymers used in PLED displays include derivatives of poly and polyfluoroester. Substitution of side chains onto the polymer backbone may determine the color of emitted light or the stability and solubility of the polymer for performance and ease of processing. While unsubstituted poly is typically insoluble, a number of PVs and related polys that are soluble in organic solvents or water have been prepared via ring opening metathesis polymerization. These water-soluble polymers or conjugated polyelectrolytes also can be used as whole injection layers alone or in combination with nanoparticles, like graphene. Phosphorescent materials. Phosphorescent organic light-emitting diodes use the principle of electrophosphorescence to convert electrical energy in Oled into light in a highly efficient manner, with the internal quantum efficiencies of such devices approaching 100%. Typically, a polymer such as poly is used as a host material to which an organometallic complex is added as a dopant. Iridium complexes such as IR3 are currently the focus of research, although complexes based on other heavy metals such as platinum have also been used. The heavy metal atom at the center of these complexes exhibits strong spin-orbit coupling, facilitating intersystem crossing between singlet and triplet states. By using these phosphorescent materials, both singlet and triplet excitons will be able to decay radiatively, hence improving the internal quantum efficiency of the device compared to a standard PLED where only the singlet states will contribute to emission of light. Applications of OLEDs in solid-state lighting require the achievement of high brightness with good CIE coordinates. The use of macromolecular species like polyhedral oligomeric sesquioxanes in conjunction with the use of phosphorescent species such as IAFA printed OLEDs have exhibited brightnesses as high as 10,000 candelas per square meter.